A fixed beam is a structural element that is rigidly supported at both ends, preventing any rotation or vertical movement at the supports. This type of beam is commonly used in engineering and construction due to its enhanced strength and stability compared to simply supported beams. Characteristics of a fixed beam. Fixed supports. Both ends of the beam are clamped or built into the supports, creating a moment-resistant connection. No rotation at supports. Because of the fixed ends, the beam cannot rotate or deflect vertically at the supports. Moment development. Fixed beams develop bending moments at the supports as well as along the span, allowing them to resist loads more efficiently. Stiffer than simply supported beams. Fixed beams exhibit less deflection under the same loading conditions compared to simply supported beams. Indeterminate structure. A fixed beam is statically indeterminate, meaning that its reactions cannot be found using only the equations of static equilibrium. Additional compatibility conditions are required. Advantages of fixed beams. Reduced deflection. Due to the restraint at both ends, the deflection in fixed beams is significantly lower. Lower bending moments in the span. The fixed ends carry part of the moment, reducing the maximum positive moment in the span. Better load distribution. Fixed beams distribute applied loads more effectively, resulting in more efficient material use. Disadvantages of fixed beams. Difficult construction. Achieving true fixity in real-world construction can be challenging and costly. Thermal stresses. Fixed supports can restrain thermal expansion or contraction, leading to additional stresses. Complicated analysis. Due to being statically indeterminate, fixed beams require more complex analysis methods, such as the moment distribution method or finite element analysis. Applications. Fixed beams are used in bridges, continuous slab structures, industrial buildings, frames in reinforced concrete or steel structures. Example: a fixed beam carrying a uniform load will have negative moments at the supports and a reduced positive moment at midspan, compared to a simply supported beam. This makes it suitable for spans where reduced deflection and increased strength are required. A continuous beam is a structural element that spans over more than two supports without hinges or joints. Unlike simply supported beams, which rest on just two supports, continuous beams extend across three or more supports, forming an unbroken line of support points. This continuity provides distinct advantages in terms of structural efficiency and load distribution. Key features of continuous beams. Multiple supports. Continuous beams rest on three or more supports, which helps reduce the bending moment and shear force at any single span. Redundancy. Because the load is distributed over multiple supports, the failure of one span doesn't necessarily lead to complete structural failure. Less deflection. Compared to simply supported beams, continuous beams generally experience less deflection under the same loading conditions. Efficient material use. The design of continuous beams often leads to a more economical use of materials, as smaller cross-sections can achieve the same strength as larger simply supported beams. Structural behavior. The presence of intermediate supports introduces negative moments, bending moments that cause compression at the top fibers, over the supports and positive moments, causing tension at the top fibers, in the spans. The bending moment diagram of a continuous beam is more complex than that of a simply supported beam, requiring analysis techniques like moment distribution method, slope deflection method, finite element analysis, three-moment equation. Applications. Continuous beams are commonly used in bridges, building frames and floors, highway overpasses, structural frames in industrial and commercial buildings. Advantages. Better structural performance with reduced bending moments. Greater stiffness leads to smaller deflections. Enhanced stability and redundancy. Improved durability due to reduced peak stress concentrations. Disadvantages. More complex analysis and design. Requires careful detailing to handle temperature effects and support settlements. Construction can be more demanding, especially in terms of alignment and formwork. In summary, continuous beams are fundamental elements in structural engineering, offering efficiency and strength in a variety of construction projects. Their ability to span multiple supports while minimizing material use makes them a popular choice in modern design. An overhanging beam is a structural element commonly used in construction and engineering, characterized by one or both ends extending beyond its supports. This type of beam is typically supported at 2 points, either both simply supported or one fixed and one simply supported, but unlike a simple beam, it has a portion that projects beyond one or both supports. Key features of overhanging beams. Support conditions. One end is often supported, while the other end extends beyond the support without direct support underneath. Common configurations. One overhang on one side, single overhang. Overhangs on both sides, double overhang. Load distribution. Overhanging beams can carry uniformly distributed loads, UDL, point loads, or a combination. The overhangs cause negative moments, bending in the opposite direction of the main span, near the supports. Applications. Widely used in bridges, balconies, canopies, and building overhangs. Useful in situations where additional clearance or unsupported extension is needed. Advantages. Provides extra span length without increasing the number of supports. Can help reduce bending moments in the midspan of the beam. Offers design flexibility in architecture and infrastructure. Disadvantages. Requires careful structural analysis to handle moments and shear forces. The cantilevered section can be susceptible to deflection or vibration if not properly designed. Bending moment diagram for overhanging beam. Overhanging beams produce both positive and negative bending moments. Maximum positive moment typically occurs in the main span. Maximum negative moment occurs at or near the overhanging support. Example. Consider a beam of length 6 meters, supported at 2 meters and 5 meters, with an overhang of 1 meter on either end. If a point load is applied at the tip of the overhang, a negative bending moment develops at the support adjacent to the overhang. Beams based on material. Beams are structural elements that resist loads primarily through bending. The choice of material significantly impacts a beam's strength, flexibility, durability, and cost. Beams can be classified based on the material they are made from. The main types include 1. Steel beams. Properties: high strength, ductile, durable, and resistant to fire and corrosion when treated. Applications: commonly used in large buildings, bridges, and industrial structures. Advantages: high load-bearing capacity, long span capabilities, prefabrication and ease of installation. Disadvantages: susceptible to corrosion, unless protected. Expensive compared to wood or concrete. 2. Concrete beams. Types: reinforced concrete, RC, pre-stressed concrete. Properties: strong in compression, weak in tension unless reinforced. Applications: residential and commercial buildings, bridges. Advantages: good fire and corrosion resistance. Low maintenance. Economical for certain scales. Disadvantages: heavy, requires strong foundation. Cracks may form under tension without reinforcement. 3. Timber/wood beams. Properties: lightweight, renewable, easy to work with. Applications: residential buildings, temporary structures, and aesthetic architecture. Advantages: cost-effective and sustainable. Easy to cut and join. Naturally insulating. Disadvantages: vulnerable to fire, pests, and moisture. Limited load-bearing capacity compared to steel or concrete. 4. Composite beams. Definition: beams made from 2 or more materials, e.g., steel and concrete, to combine beneficial properties. Applications: bridges, high-rise buildings. Advantages: Combines high strength and good compression. Optimizes material usage. Disadvantages. Complex design and construction. Requires precise execution. 5. Aluminum beams. Properties: lightweight, corrosion resistant, and relatively strong. Applications: aerospace, marine structures, temporary frameworks. Advantages: lightweight and portable. Resistant to corrosion. Disadvantages: expensive. Lower strength compared to steel. 6. FRP, fiber reinforced polymer, beams. Properties: very lightweight, non-corrosive, and high tensile strength. Applications: marine, chemical plants, retrofitting existing structures. Advantages: resistant to chemicals and moisture. Lightweight with high strength to weight ratio. Disadvantages: expensive. Brittle compared to metal beams. Conclusion: the selection of beam material depends on structural requirements, environmental conditions, cost, and aesthetic needs. While steel and concrete are preferred for their strength and durability in large-scale structures, timber and composite materials offer advantages in flexibility, sustainability, and innovation in modern construction.